A very good evening, everyone. Welcome to day 5 of Adult Faculty Development Program on AI in Action, Bridging Theory and Practice in Data Science and Deep Learning, organized by the Department of Computer Science and Application, St. Mary's College Autonomous, Thrissur. Let us begin today's proceeding with a moment of silent prayer. Thank you, dear participants. Before we begin, a gentle reminder. Please keep your microphones muted and cameras turned off during the sessions. Kindly use the chat box to post your queries. A minimum of 80% attendance and feedback submission are mandatory for the certification. Participants must secure at least 70% marks in the assessments conducted during the program. We request your cooperation for the smooth conduct of the sessions. Today, we are privileged to have two insightful sessions focusing on deep learning-based speech processing. The first session will introduce us to the foundations of speech processing using deep learning, and the second will be an engaging hands-on session that will help us apply these concepts in practice. Both sessions will be handled by our distinguished resource person, Dr. Rajeev Rajan, Professor and Dean, Research, Government Engineering College, Idukki, an eminent academician and researcher with extensive expertise in speech processing and deep learning. I now invite Ms. Gigi M. Anthony, Assistant Professor, Department of Computer Science and Application, to kindly introduce our esteemed resource person, Dr. Rajeev Rajan. Miss, please.
Good evening, everyone. It's my privilege to introduce Dr. Rajeev Rajan, Professor and Dean, Research, Government Engineering College, Idukki. Dr. Rajeev is an eminent academician and researcher with vast expertise in speech processing and deep learning. He holds his PhD in Computer Science and Engineering from the Indian Institute of Technology, Madras, with his research focusing on the field of audio processing. He completed his MTech in Applied Electronics and Instrumentation from the College of Engineering, Trivandrum, and his BTech in Electronics and Communication Engineering from the College of Engineering, Adur. Adding to his academic accomplishments, he also pursued a Master of Business Administration in Operations Management from IGNOU. His journey as an educator began as an assistant professor in electronics and communication engineering at Government Engineering College, Wayanad. He has debuted for higher studies at the Indian Institute of Technology, Madras, where he completed his PhD. He resumed his teaching career at Government Engineering College, Wayanad, and later served at the Rajiv Gandhi Institute of Technology, Kottayam. Beyond academia, he also has a valuable research and industrial experience, having worked as a senior research fellow and radiological safety officer at the Fluid Control Research Institute, Palakkad, an institution under the Ministry of Heavy Industries, Government of India. He also has demonstrated his innovative spirit through patent fields, including Psychoscraper, a device to study algae characteristics, adaptive trolley, e-drive in collaboration with SES IT Trivandrum, and ultrasound guided needle injector, also developed collaboratively. He is also a prolific researcher with 31 publications in reputed journals. His research interests and thrust areas reflect his passion for innovation and multidisciplinary exploration. They include audio, speech, and musical signal processing, hearing, image processing, and natural language processing. His excellence has been recognized with several awards and honors, including serving as chair at InterSpeech 2024 in Kos, Greece, receiving the P.T. Bhaskar Panikar Science Writing Fellowship 2022 from KSCST, winning the Best Paper Award at the Kerala Science Congress 2023, the Outstanding TA Award from IIT Madras, representing IIT Madras in the ASV's Proof 2017 and the Spoofing Challenge, where the team secured the 17th position out of 50 countries. He secured first rank in MTech 2004 at Kerala University. With such a remarkable academic background, innovative research contributions, and national as well as international recognition, he truly stands as an inspiration. We are privileged to welcome Dr. Rajeev Rajan to this gathering. Hearty welcome, sir.
Thank you. Thank you. Slides are visible, right?
Yes, sir.
Okay, thank you. So I express my sincere gratitude for having invited me for today's session. I think for the last 4 days, you might have studied some of the basics related to deep learning and varying from different architectures to transformers. And first day, you learn about the foundations of ML, and successively you have gone through various architectures, DNN, CNN, transfer learning, and transformers. So I think today we are going to apply this deep learning framework on one domain, that is speech. So some of you might have worked in speech, some of you might have worked in image. Now let's start today's session. So as you know, we are going to study speech signal processing. Broadly, is a class of signals. So now let's go on through various signals first. You can see 3 representations in this slide. First one is a one-dimensional signal. That means x-axis time, y-axis is amplitude. It's a one-dimensional signal. So it is defined over time. Amplitude varies continuously with respect to time. We have a number of examples like sensor data or acoustics data, vibration data, speech data. All come under the first category, that is one-dimensional signal. When you add one more dimension, that is in spatial coordinates x and y, it becomes two-dimensional data. Example is image. Okay, in this case, there will be 2 coordinates x and y. So and the values, the pixel values will be placed in this 2-dimensional signal. It will become image. So when it goes to when we add time as one more variable, okay, for example, so it will become it becomes a 3-dimensional signal. That means we add time as one more dimension. It becomes a 3D signal. So you can apply various deep learning framework in any of the signal. For example, if you apply deep learning techniques in one-dimensional signal, in our case it is speech, you can go for speech recognition, speaker classification, speaker recognition, or speaker enhancement, whatever it may be. You can apply deep learning there. In the case of image, similarly, you can go for image recognition, image analysis. In the case of video, that means object tracking, anomaly detection. In all this application, you can use deep learning. Okay. Today we concentrate on the first domain, that is first type of signals, that is a one-dimensional signal called speech. Okay. Now let's have an introduction about the speech production mechanism first. Then we will go for the different features that can be extracted from the speech. Successively, some of the framework using deep learning. I think got what I mentioned till now. So, what is speech? So we express our thoughts and feelings Okay, using our articulators. Articulators means some of the organs that play together to make sounds. Okay, they start from lungs, larynx, jaw, tongue, lips, etc. Okay, so when they work together, we can make any of the sounds. So these are the articulators that play important role in making speech. So I will draw one figure. Okay, now let's see how speech is produced. See here, you can see two tracts. This is nasal tract. This is nasal tract, and this one is vocal tract. So when sound comes from here, one organ is there, that is vocal cord. Vocal cord, and this goes to lungs. So when air puffs push, and it goes through this vocal cord, then vocal cord vibrates. It will vibrate. So when it is vibrated, impulses, the train of impulses. So opening and closing, right? Opening and closing. Open, close, open, close. So this air puffs will be pumped to this area. This is our mouth. Okay. The frequency of this impulse is called pitch. This is called pitch. This is the time period, pitch time period. So the pitch is the vibration of the vocal cord, the fundamental frequency of vibration of the vocal cord. Okay, that is pitch. So when we listen to various music, we sometimes say that the pitch is the pitch of that listener is very high. Okay, otherwise pitch is very low. That means it indicates the vibration of your vocal cord. Okay. Usually there is a particular range. For female, it goes to it can go up to 250 hertz. 250 hertz. That means maybe 120 to 250 hertz. For males, it goes to 80 to 150 hertz. And for infants or kids, it go up to 400 hertz. So this is the range of pitch. That means the pumping frequency of air puffs to our mouth. So these are the pitch ranges. So that means the pitch variation, otherwise pitch frequency of females are very high as compared to men. Okay. So now when it comes to our mouth, there are different organs that plays together to make various sounds. Okay. That means the jaw is there, tongue is there, our lip is there. Okay. So they play all together to make various sounds. So when they move, the cross section varies. Assume this is the cross section for making a sound K. So maybe this is the cross section, it making P. Assume maybe this is the cross section you make for some other sound, yes, whatever it may be. Okay. So when this cross section changes, you are able to making various sounds. So you can make an analogy of various pipes connected together like this. You see this? Some circular pipes. So almost the shape of this cross section. So this is one tube, this is second tube, this is third tube. Usually this type of analysis is called tube model analysis. We have used 3 tubes to mimic the behavior of our mouth. Okay. So each tube has its own frequency. It called Foreman frequency. This is F1 and this is F2 and this is F3. So F1, F2, F3 are the resonance frequencies of these tubes that constitute the area. Okay. So that means F1, F2, F3 of this structure is different. F1, F2, F3 of this structure is different. F1, F2 and F3. So when you make various sounds, your F1, F2, F3 varies. Pitch is called F0. Pitch is called F0. So now we have 3 frequencies. F0 is called pitch. F1 is the first Foreman frequency. It is called Foremans. Usually called Foremans. So you have come across 2 terms. One is pitch. Second one is Foremans. So F1, F2, F3, the variation of F1, F2, F3 makes variable sounds. Okay. Another thing is you can see one more track. It's called nasal tract. So usually the vocal tract for a healthy person, the vocal tract starts from this vocal cord to lips. It is 17 centimeter. For a healthy person, the vocal tract length. Vocal tract means the tract starts from your vocal cord and ends in your lips. It is 17 centimeter. There is one opening in the top. The top palate, there is one opening. So when you make some sounds, nasal sounds like M, N, ing. So when you make these sounds, your lips are closed. Okay, your lips are closed. Then this opening, this is called velum. This opening is called velum. This velum will be opened and air will go through your nostrils. Okay. So this is called nasal tract. So some of the sounds are produced through your vocal tract. Some sounds are produced in your nasal tract. So this is the basic fundamentals of speech production. So I shall summarize. That means air puffs come from your lungs. It will force the vocal cord to vibrate. Okay, opening and close, opening, close, opening, close. The fundamental frequency of this vibration is called pitch. And when this impulse train then enters to our mouth, okay, so there are various organs which make you to pronounce various sounds. So when you make an analogy of tube models, assume we are using 3 tubes to model your mouth, otherwise vocal tract. So the resonance frequencies of that tubes are called formants. So F0, F1, F2, F3 makes various sounds. Okay, and some sounds are coming through your nostrils. They are called nasal sounds. Some sounds are coming through your vocal tract, and they are fricatives, affricates, plosives. So various subdivisions are there. I'm not going in detail. So this is the basic fundamentals of speech production. Okay. Now let's go back to our slide. Okay. Okay, this is the, I have given two plots here. The top one is the pitch extract, because pitch is continuously changing. When you talk something, when you speak something, your frequency of the vibration of your vocal cord changes continuously. That is, so the second plot, the top plot is the speech. Second one is the pitch track. That means continuously pitch is changing. Okay. At the bottom pane, you can see three lines. The bottom one is F1 and F2 and F3. That means you are making various sounds continuously. When you speak something, you are pronouncing various sounds. So when you make sounds, you are when you pronounce different phonemes, it's called a basic unit of speech. Your vocal tract changes its shape. Whenever its vocal tract changes, its resonance frequency changes. So you can see that continuously your resonance frequency F1, F2, F3 changes, because the three tube models, F1, F2, F3 changes, you are able to make various sounds. When various sounds are connected together, it becomes words. When words connected together, it becomes speech. That is a process. Here on the right side, you can see it is a 1, 2, 3, 4, 5, 6, 7 tube model. So there will be 7 formats. Okay. Usually F1, F2, F3 are that much important. So F4, F5, F6 are not that much important. So in this bottom plot, we use only 3 tube models. You can extend to several tubes. That means piecewise connecting various tubes like this. So this is a tube model analogy of our vocal tract. Okay. Now let's. I will play one video. How this how our vocal cord vibrates. So now let's okay, sides are visible, right?
Sir.
So this is now let's see what is the difference between speech and music. Okay. So as you know, speech signal usually in the bandwidth of 4 kilohertz. When it goes to music, it can go up to 8 kilohertz bandwidth. It can go up to 8 kilohertz bandwidth. That's the difference between speech and music. Okay, now let's see. We have gone through basic speech production mechanism. Now we have speech. What are the various applications of speech? So here I have indicated various applications like speech recognition, text to speech, that means speech production, speech synthesis. You can synthesize speech, that means you can generate speech. Next is language understanding and language generation, speech coding. So there are various applications in speech domain. So let's see one application, that is speech processing, is a speaker recognition. As the name tells, speaker recognition means it identifies a speaker. So recognize a speaker. As the name tells, it is recognizing a speaker. So in speaker recognition, there are two tasks. One is speaker verification. Second one is speaker identification. Speaker verification means identify whether the speaker's claimed identity is true or false. For example, is it Bob's voice? That means you are giving a claim. So answer is yes or no. Speaker verification system. That means whenever you verify a document, you always give an original, right? An original. So we check with the original document and we verify. Similarly, in speaker verification, you will give a speech sample, then you will ask such a question: is this Ram's voice? Is this Bob's voice? So answer is yes or no. That is a speaker verification task. When it goes to speaker identification task, only speech sample will be given, and you have to identify the person whose voice is that. Okay. So that's a task of speaker identification system. So speaker recognition broadly can be classified into two. One is speaker verification, and second one is speaker identification. Speaker verification is a process of identify the claimed speaker. That means you whether a speaker's claimed identity is true or false. Answer is yes or no. That means if you supply Bob's voice and ask, is that Bob's voice? Answer is yes. Otherwise, no. In speaker identification, speech sample will be given. You have to identify the name of the person. Is it Ram or Geeta, whatever it may be. Okay. So this is the basic building blocks of a speaker recognition task. As you know, there are two blocks. First one is feature extraction. Second one is model training. And feature extraction means you cannot directly supply speech to a model. So you have to extract some features. In image recognition, you supply image as such to a neural network. The neural network will extract your features. But in speech processing, you have to extract some features. They are called handcrafted features. You have to extract some features. You have to supply these features to your model. So feature extraction is a front end, and the back end is a model. That can be a machine learning model like support vector machine, or deep learning models like DNN, or convolutional neural network, or transformers. You can use any of the architecture in the second block. So there are two blocks. First one is feature extraction. You can extract various features like spectral centroid, spectral roll-off, or prosodic features. Various set of features you can extract, and you can give these features to the model. Okay, so model will be trained. So training and testing are the two part. So for the speaker recognition task, first you will extract these features and use these features to train the model. Okay, in supervised learning, you train the model with labels of the speakers. Once you have trained the model, you will use this model to identify the speaker. Okay, so you will extract during testing phase. You will extract the same set of features as that of the training phase. Then you will give these features to the model. The model will take will do the decision. Okay, that is the process. So speaker verification or speaker identification task consists of a model building. So for building the model, you need features. There are various, I have said various features are there. Take that features, extract that features from the speech signal, and given to the model for training. Okay. In nowadays, there are end-to-end models. Okay, the new development is end-to-end models. END-2-END. Okay, end-to-end models means no need of this feature extraction phase. That the model itself will extract features from the raw audio. This is called raw audio. So the recent development is skipping this feature extraction block. So in image processing, we directly give image to the model. Okay. There we do not extract features, but in speech we should extract features. But nowadays there are end-to-end models. That means raw audio will be supplied to the model itself and do a unified training, and the model will extract the features and do the training process. Okay. So now let's see the various features. I have listed around 5 set of features here. Okay. Whenever you read a speech processing paper, speech related paper, you definitely will come across these type of features. First one is acoustic features. That means extract features by doing a window analysis on the signal, speech signal. It's called acoustic features like MFCC, male frequency capsule coefficient, known as linear predicting capsule coefficient, modified group delay features, prosodic features. These are the various set of acoustic features. Now next is texture features. Texture means musical texture. Whenever we go to a shop for purchasing our dress, we usually say that the texture is good. Okay, the texture is good. That means that color combination is good. Similarly, similar to that of that material in speech also, and the speech signal also, some features play an important role to define its texture. It's called rhythmic features, timbral features, melodic features. You can extract all these features using various tools. Various tools are available. Especially these texture features are very much useful in music analysis. In music analysis, your rhythm may change, your melody may change. So these type of features are very much useful in speech analysis. Sometimes in direct recognition, whenever you travel from north to south of Kerala, because the speaking style is various, right? Speaking style varies from one end to other end. In such cases, the rhythmic features are very much important in recognizing various dialects. That is a texture features. Next is visual representation. Definitely, you can convert your audio signal to image. Okay, then you can apply all the image processing there. So that's an interesting thing, because in the speech can be converted to an image. That is a visual representation. That's called spectrogram, morgidiogram, tempogram, and you can apply all the image processing tasks to this speech once you converted the speech to an image. That's another representation. Next is textual features. See the difference between texture and textual. Textual features means the features that extracted from the words. Okay, TF-IDF, word to work. Whenever you make some, whenever you use some particular word, okay, that word can be that words are converted to vectors. Okay, so your content, your speech content is very much important in textual features. Okay, in the first 3 features we have seen the signal variation, but in the case of textual features we always concentrate on the content. Okay, that means each word can be converted into various vectors. These vectors will be used as the representative for those words, and you can use for classification or whatever be the task. The other category is high-level features. That means some modeling approaches like I vectors, X vectors, D vectors, C vectors, etc. These are highly modeled vectors representing speakers. These are I vectors, X vectors, etc. For extracting all these type of features, you have various tools like Librosa. Librosa is one tool. Librosa, it's a Python tool. You can use these tools to extract these type of features. Okay, so features are the front end in any classification task. The back end is the model. So you studied all the back end models for the last 4 days. This is the front end. Back end models like deep learning or machine learning models you can use. So these are the various features. For this time being, I will explain how to extract one feature, that is MFCC. This is our speech signal. This is your speech. How will you extract one feature here? So you need to convert this to some numbers. Assume we are going to extract MFCC. First, you will make some frames here like this. This is the first frame. This is second frame. This third frame, and this is fourth frame, and this is fifth frame. First, second, third, fourth, and fifth. Sorry. So instead of taking entire signals as such, we take short frames and we extract features. That's the difference between image and speech processing. In speech processing, in image processing, we simply feed this image to the net. But in the case of speech processing, just we do a frame-wise analysis. Assume this is first frame. Just take the first frame. This is the first frame. And this is the second frame. Extract features from the first frame. Okay, assume it is MFCC. This is this frame number 1, 2, 3, 4, 5. Assume in this speech there are 5 frames. Extract some features. Assume apply some mathematical equations. You extract some features 0.8, 0.2, 0.3, 0.4, etc. In the second frame, you extract 0.85, 0.25, 0.35, 0.4. In the third frame, 0.08, 0.001, 0.10, 0.20. The fourth frame, 0.1. Assume some numbers. So now you converted this one-dimensional signal into a 2D matrix like this. Just see that. You parameterize speech. This is called parameterization of speech. If there are 100 frames, there will be 100 rows and that much of dimensions in the rightward directions. Okay. So this is called parameterization of speech. So it's very important that as different from image, in speech we extract features by dividing the entire speech into small chunks. Okay, some 30 milliseconds. Usually we use 30 milliseconds. Usually we use 30. The frame width is 30 milliseconds. 30 milliseconds. Next 30 milliseconds. 30. We usually give an overlap. The specific reason is there. I won't mention for the time being. It may take some time. That's why. So we give some overlap of 10 milliseconds. So we take 30 millisecond timestamp. We extract features. Next 30 millisecond. Next 30 millisecond with overlap of 10 millisecond. We extract those features. We stack in the form of a matrix. Then this numbers will be supplied to the neural network. So instead of this speech signal, this is called parameterization. Depends upon the applications. You can extract various features. As I mentioned, MFCC or LPCC, whatever it may be. So this is the basic fundamentals of feature extraction from speech. So this is the right side. You can see the block diagram for extract MOCC. MOCC is actually very much important in speech processing. Mel frequency capsule coefficient. It is called Mel frequency capsule coefficient. It's very much important features in speaker recognition, speaker diarization, speech recognition. Whenever you see a paper in speech, definitely you will come across this term, MOCC, that is called male frequency capsule coefficient. Okay. The steps to extract MOCC is given in this slide. That is, break the signal into overlapping frames, take Fourier transform, passing through a filter bank, take log, and take FFT. You will get some coefficient. You see in the bottom, there is a 2D matrix. In the left side, there is a speech. You see that an audio signal is converted into a 2D matrix through these type of steps. Then you will get MOCC. So the MOCC will be supplied. MOCC will be supplied to the system. So this is just one step. As I mentioned, there are various features. You see, I mentioned only MFCC. There is separate steps to LPCC, mode GDF, and prosodic features. Depends upon the application. In some application, MFCC is very good, you will extract MFCC. In some application, LPCC is very good, then you will extract LPCC. In some other application, rhythmic features are very much important, you will extract those features. So definitely there will be some blocks, some steps to extract those features. One important thing is, as I mentioned earlier, the features are extracted frame-wise. The entire speech is entire music piece or entire speech piece, speech signal is divided into small chunks, because we make it stationary. We make it quasi-stationary. Then we will extract those features for various speech processing tasks. Okay. Now this is a texture feature. Like just see here, timbral features, rhythmic features, melodic features. So these are various features I extracted for a music piece. Spectral centroid. Rhythmic features is the rhythm shows the speed of the music, pace of the speech, or pace of the music. That's called rhythmic features. Melodic features means it related to the predominant melody, predominant pitch of the music piece. Just see, this is a visual representation of speech. Definitely you can visualize speech. The left side, it is speech signal. You convert it into corresponding images. Okay, various representation. Speech or music, you convert it into spectrogram. Spectrogram gives the various frequency component present in this signal with respect to time. You see this, the x-axis is the time, y-axis is the frequency. So various frequency component present in the one-dimensional signal. Now you converted this 1D signal into a two-dimensional signal. So you can apply all the speech image processing methodology on this visual representation. Another one is tempogram. Tempogram shows the pace of the speech, or pace of the speed of the music, or speed of the speech. Another one is mode GD-gram. It corresponds to the Fourier transform phase of the speech. Okay, so there are various visual representations. The important thing is you can visualize speech. Can we visualize speech? Yes, we can visualize speech. And you can use this visualization, various visual representation for various classification, maybe speech process, speech recognition, or speaker recognition, or singer identification, raga recognition in music. Okay, in motif recognition, whatever it means, you can use those. You can do that type of task using visual representation. Okay. This is spectrogram, and Mel spectrogram. Another variant of spectrogram is called Mel spectrogram, and the tempogram. Tempogram gives the speed of the music. Okay, tempogram gives the speed of the music. This is Okay, actually, I missed this point, I feel. So we have studied about various architectures like deep neural networks, convolutional neural network, LSTM, transfer learning, transformer in the previous 4-day training program. So I'm not going into detail all the networks. Just I will take some 2 to 3 applications, and we will go through the results. Okay. First, so let's see various sounds. Like we discussed about musical textures, like musical textures. So there are 4 types of musical pieces: some monophony, homophony, polyphony, and heterophony. So I will play those textures.
Musical texture is the element of music that analyzes musical layers in terms of number and function. The most basic texture is called monophonic. Oh, mama, I feel for my life won't go long, Monophonic texture has only one layer, a melody. With monophony, it doesn't matter how many instruments and or voices are present, as long as they are all singing or playing the same thing at the same time. It also doesn't matter if the voices or instruments are on the exact same frequency or if they are singing in octaves. An octave is the distance between 2 musical pitches that sound almost the same, but one is higher and one is lower. It also doesn't matter if drums are present or not. In most cases, drums, the rhythmic layer, are neither melody nor harmony, and therefore are generally not considered when determining texture type. Too much monophony can be boring, so most music has another kind of layer, harmony. When a melody is supported by a harmony, the texture is homophonic. No one may ever know the feelings inside my mind. All of the lines are in the right, running out of time. One layer grabs your attention, and the other layer is just hanging out in the background. Most popular music is homophonic. Texture. Polyphonic texture can also occur if you take the same melody but start it at staggered intervals. This is called a round. The last texture is called heterophony. Heterophony is relatively rare in Western music, but it's very common in non-Western music. It occurs when there are 2 or more versions of the same melody happening at the same time. Usually, one of the melody lines has more notes than the other, a kind of musical decoration, and or a slightly different rhythmic pattern. Songs will often use a variety of textures to keep the piece interesting. For instance, this song has monophony, homophony, and polyphony. Start trying to find the musical textures of your favorite music.
So we have seen the various textures. Okay, we discussed about the texture features. So it can be monophony, it can be homophony, it can be polyphony, or it can be heterophony. Okay. So now let's see some of the musical tasks like a classification. You can do a singer identification task, identify the singer. You can do genre classification. You can recognize the predominant instrument from music. You can identify raga of a music. You can identify various moods. Okay, and you can design music recommendation system. Okay, so there are various applications. Okay, definitely the music is an extension of speech. So there are various applications for deep learning in music and speech domain, like a source separation. You can remove some unwanted signals. You can synthesize speech. You can generate song from some lyrics. Okay, so there are various applications. Actually, these applications are the outcomes of the developments in deep neural network. Okay, various deep convolution networks. And so the recent studies, in every day, new architectures are coming up. So it has their own advantage. Researchers are coming with a new architecture. They are using these architectures for various tasks in speech and music processing. Okay, so we have done one work as part of our research. That is, in this case, okay, there is one category called octoechoes. This is one music genre. In this case, there are 8 types. That means you can sing a set of lyrics, same lyrics in 8 types. It is called niram. Okay, it is called niram. That's why it's traditionally called octoechoes. In the previous case, we have seen that texture is different. Okay, various music styles, texture is different. In this case, your text is same. That is, your lyrics is same, but your music is different. Just see this. I will play this sound.
സുവിശേഷത്തിൽ കീർത്തിതരാ പരിശുദ്ധന്മാരേ ഭാഗ്യം ജീവഗ്രന്ഥ സുവിശേഷത്തിൽ പരിശുദ്ധന്മാരേ ഭാഗ്യം ജീവഗ്രന്ഥ വിശേഷത്തിൽ കീർത്തിതരാ പരിശുദ്ധന്മാരെ ഭാഗ്യം ജീവ വിശേഷത്തിൽ കീർത്തിതരാ പരിശുദ്ധന്മാരെ ഭാഗ്യം.
So in this case, you can see that text is same, but music style is different. So what type of features you will be using for this task? So in the bottom, you can see a spectrogram of this music piece. There are 8 classes. Your spectrograms are different. So you cannot use textual features. That means word to work or TF-IDF, those features are not at all helpful in this task. In this task, you can use visual representation or acoustic features. So the important thing is depends upon your application. Okay, in which application you use these features is very much important. You cannot simply say that this feature is apt for all the applications. No, that means as your aim changes, your feature set changes. Okay, in this case, as I mentioned, text is different, but 8 types of songs. For classification of this genre, you have to go for some music texture features or acoustic features. Okay, just I mentioned the importance of features when you do speech or music classification using deep neural network. Okay. Now let's see. So I mentioned about textual features. In some cases, you need textual features. That means your speech is converted to text. Okay, your speech is converted to text, then text is converted to numbers. In some cases, you can go for textual features. Okay, the previous application, we cannot go for textual features. We can only go for texture features, music texture features. Okay, there are various textual features, TF-IDF and word to work. Okay, these are the various approaches to convert your speech into text and text into numbers. Okay, I will just play one example where these textual features are very much important. Okay, you know about the Tiruvadira dance. Okay, Tiruvadira, very famous dance form in Kerala. So in Tiruvadira dance, there are 4 segments: Stuti, Padam, Kummi, and Mangalam. Okay. In these segments, for example, in Stuti segment and Mangalam segment, specific words will be repeated. Okay, specific words will be repeated. So those words can be used to segment those regions. For example, if you want to listen to Padam, okay, no need to waste the entire time for listening to the entire piece. Just use some machine learning or deep learning techniques to segment this music piece and just pick maybe Padam. Okay. So in this case, textual features are very much important. Why? Some of the terms will be played repeatedly in each segment. So you search for those terms and segment those regions. Okay, just see this.
Please subscribe our channel. Don't forget to share, comment, and like. Don't forget to share, comment, and like.
So in this case, it may be some maybe 45 minutes or 15 minutes performance. So you want to segment those the entire performance into various segments like Stuti, Padam, Kummi, or Mangalam. So you can segment using textual features. This is an important task. The music or speech segmentation. Okay, you can use deep learning here. So I will play. This is the Stuti segment. So in Stuti segment, some specific terms will be repeated. Just search for those terms. Then if you recognize those terms, just label those segments as Stuti. So in this case, textual features are very much important. So as your task varies, your feature sets varies. Okay, now it's called melody extraction. The other task is melody extraction. Melody extraction means automatically estimating the predominant pitch. Okay, whenever you listen to a music, if somebody asks you to hum the piece of music you listen, you make some sounds like that. Means there may be some accompaniments. Okay, even though there are accompaniments, you make some sounds, some monophonic sounds. These are the essence of your essence of that music. Okay, what is the advantage of extracting this essence? That means in a repository, if you want to search for a particular music piece with which align with your tune, you can go for searching. Okay, you can go for audio search. It is called query by humming. That means just search that music piece with this monophonic sequence, like then this melody will be searched, okay, in the repository, and it will retrieve all the musics that match with this tune. So there are various applications for this melody extraction, as I mentioned. Okay. So this is the you can see 3 plots here. The left side is the polyphonic music. In polyphonic music, many accompaniments will be there, many pitch tracks will be there. Only one lead singer is there. You need the pitch track of the lead singer. You can apply some algorithms to extract the pitch of the lead singer. You can use this pitch to search in the repository. In the right side, you can see the pitch track of the lead singer. Okay, you apply some deep learning methodology to extract this pitch track. This is called melody. You apply this melody for various applications like music search or query by humming. Okay. Now I see. Now I will show the some melody extraction tags. I will play the original sound here. Original sound. Just listen here. Just original sound.
We never saw you, I already knew there was something inside of you, something I thought that I would never find. Angels.
So this is the original sound with various accompaniments. I want to extract the melody. Just see the melody here. So you apply some deep learning methodologies to extract this melody. So later you can mix with various. Similarly, this is another sound, another music piece, the polyphonic music.
Gone away. Get hard of my fancy. Oh,
So this is a polyphonic music with various accompaniments, but lead singer is there, and this is the pitch of the lead singer extracted from deep learning methodology. This is another one. So when you extract the pitch. So this monophonic pitch sequence, that means this tune is actually using deep learning technologies. Okay, so when you give this extracted pitch track to a repository, the machine will be will give you various music pieces that match with the tune of the melody. So that's a very interesting application of deep learning in music signal processing. Okay. So just see the. This is the one step. I will just explain one step for melody extraction using deep convolutional neural network. This is the one method proposed by Sanjun Kum in 2017 to extract melody of the music. There are two legs, okay, two streams. One is for extract melody, and the second one is extract voice and voice. That means if there is no melody in the music piece, you should the system should give 0 value. Okay, it should not give any noise values. So the spectrogram, that is visual representation, is the input to the two networks. The top leg, it is a deep convolution neural net for extract melodic pitch. The bottom leg is to extract noise, that is voice activity detection. It is called. That means if there is a melody, the value should be given as the detected melody. Otherwise, if there is no melody, if there is no music, it should not give any noise. It should give 0 value. It's called voice activity detection. So the spectrogram is the input. Okay, spectrogram is the input, and the deep convolution neural networks are trained to extract pitch melody contour. Okay, this is the details. You can refer to this paper, classification based singing melody extraction using deep convolution neural network. Now let's go for source separation. Let's wind up within 10 minutes. Another interesting task is source separation. Source separation means assume in a meeting there are two conversation between 2-3 people. So you want to extract the speech of a particular person. You want to suppress other speakers' voice. You can go for source separation. In music also, if you want to remove some of the instruments from the polyphonic music, you can go for source separation. Just see one example here. Is a mixed sound. This is a mixed sound. So there are various musical instruments like trumpet. So you want to extract trumpet sounds only. Just see here. This is the extracted using deep learning methodology. So from the mixed signal, you extract the trumpet sound only. Okay, trumpet instrument. The other one is here one lead voice is there, accompanied by some instruments. So you want to extract lead voice. So in this case, you use a deep learning methodology to extract some source. Okay, some mixed source. Okay, this is another example. So in the original recording, one soprano music, that means your pitch range is very high. Okay, you want to separate that singer voice, and you have to change the pitch and you have to mix again. Okay, just see that. This is the original sound, original recording. So here, one soprano music, that means pitch is very high. So you want to separate its soprano. So you removed that accompaniments, you extracted that the lead singer voice. Again, what we do is just pitch shift the pitch to a lower scale and again mix. So from the original recording, you extract some lead singer voice. You change its pitch range. you again remix it. So you can do this. And one algorithm is I mentioned here. This is cycle GAN. It's another neural network architecture that can be used to do this source separation task. Okay. Here also we use spectrogram, and we use cycle GAN, generated adversarial network. Cycle GAN is advanced GAN network that can be used for this purpose. Okay, predominant source separation. We are using spectrograms. We use some pitch tracking algorithm. We use binary mask and some training on the cycle GAN network. Definitely, you can extract a particular source from a mixed sound. Okay. In this case, we have used cycle GAN. It's a neural network architecture. Cycle GAN has been used to extract the predominant source. Okay. This is our experiment only. So we published a paper on this. Okay. And there is a singing synthesis. That means you have some lyrics. You want to give some tune. Okay, that is multi-voice singing synthesis from lyrics. You have written some lyrics. You want to give music. So no need of any musician. You can do that. That is the process. So lyrics, first the lyrics will be converted to speech. Then speech will be converted to singing. That is a two-stage process. Just write your lyrics, scan those lyrics, give to the system. System will convert those lyrics to speech sound. Okay, in your voice. If you have some speech sample, so that speech will be given by the system in your voice. That is a multi-voice singing synthesis. And the singing means the singing voice will be given in your sound. That's an interesting thing. That means just you give lyrics, the lyrics will be converted to speech. That speech sounds as you speak. As you speak, then that speech will be converted to music as you sing. That's a very interesting application, and that can also be done using deep neural network. So I will go to the building block. I will go through the building blocks of such a system. So this is the building block. There are 3 blocks. First one is the TTS module, text to speech. Text to speech, that your text is converted to speech. That is a top block. The bottom block, speech to singing. That means your speech is converted to singing. And the third block is to enhance the intelligibility. Intelligibility can be enhanced using a separate module. So there are 3 blocks, mainly 2 blocks. We added one more block to enhance the intelligibility at the end, in the back end. So TTS module. In the TTS module, input is a text and output is a speech. In the STS module, the speech from the TTS module will be given to the STS module, and the output is a song. And the intelligibility can be increased using the intelligibility enhancement module. So in this case, you have to give some speech samples, okay, for getting a song in your voice. That's an interesting thing. This is the connections. This is the deep neural network architecture that can be used to synthesize songs from the lyrics. Just I will show one example. This is the text, okay, dashing through the snow on a one-horse open sleigh. Okay, this is one text. First, I will convert it into speech.
No. In a one-horse open sleigh.
That means this text is converted to speech. Now just see the song. That means here you synthesize song from lyrics without the help of any person. Okay, this is a female voice. Just see the male voice.
Dashing through the snow in a one-horse open sleigh.
That means your text is converted to speech. It's a synthesized speech. Okay, and then you convert it into music. So here, without any human intervention, you converted a text into music with some available speech samples. If I have some speech sample of yours, I can use that speech sample to generate any of the song with my own lyrics. Okay, let's see another one. Twinkle, twinkle, little star, how I wonder what you are. Okay, I converted this text into speech.
How I wonder what you are.
So next, let's see the song.
Twinkle, twinkle, little star, how I wonder what you are. Twinkle, twinkle, little.
So the female voice now.
Twinkle, twinkle, little star. How I wonder what you are.
And this is automatically generated without any human intervention.
Twinkle, twinkle, little star, how I wonder what you are.
So you can use various deep learning methodologies for this type of tasks. So in summary, so I'm going to conclude. Actually, we have gone through a speech production mechanism, how speech is produced, and some of the terms like pitch and formants. Pitch is a fundamental frequency of vibration of your vocal cord. Formants are the resonance frequencies of the tubes that create your mouth, that create your vocal tract. Okay. So whenever you make any sounds, your formants will be changed, and you can make various phonemes, various sounds using this, using various shapes of your vocal tract. Okay, this vocal tracts, the shape is changed due to the movement of articulators like jaw, lips, tongue, etc. Okay, so some of the sounds are coming through the nostrils. Those sounds are called nasal sounds like m, n, and ing. Some sounds are coming from your vocal tract, and those categories are fricatives, affricates, plosives, etc. Okay, then we have gone through various feature sets. Okay, in any classification task, there will be two blocks. First one is feature extraction. Second one is deep neural network. And depends upon the task, you can fix your features. You can extract those features frame-wise. You can supply these features to the backend neural network. Neural network will do the task. If it is a classification task, or if it is a synthesis task, or if it is a source separation task, it will do when you feed those important features, particularly for a specific task. Okay, we have seen various tasks like a speaker recognition task. We have seen. Second one is we have gone through melody extraction, application of melody extraction. We have gone through source separation. We have gone through singing voice synthesis. Okay, so then we have gone to two architectures. First architecture is for melody extraction, using using deep convolution neural network. Then we have seen the DNN architecture for singing synthesis. Okay, source separation. So by this I wind up first session. Over to you.
Thank you, sir. Dear participants, we will pause here for a short break. We will be back in 5 minutes with the hands-on session. Thank you.